This is chapter 8 homework. And we are going to solve problems 1, 3, 5, 11, 14, 20, 35, 48, and 62. Let's begin. Number 1 reads, what is the magnitude of the momentum of a 10,000 kilogram truck whose speed is 12 meters per second? That's A. And what speed would a 2,000 kilogram SUV have to attain in order to have the same momentum, the same kinetic energy? All right, momentum is defined as m times v, so that's going to be 120, right? Kilograms meters per second squared. 120,000, I'm sorry. 1.2 times 10 to the 5th kilograms meters per second, not second squared. You'll have to excuse me, it's early in the morning. Anyway, moving on. All right. So now what speed would a 2,000 kilogram SUV have to have in order to have the same momentum? So we're going to do P divided by M equals V. So 1.2 times 10 to the 5th kilograms meters over seconds divided by 2,000 kilograms is going to give me 60 meters per second. Now we need to find out the speed that SUV would have to have in order to have the same kinetic energy. All right, E sub K is going to equal to 1/2 mv squared. So we've got 1/2 times 10,000 kgs times 12 meters per second quantity squared. And we want to set that equal to 1/2 times 2,000 times v squared. So these halves go. And now I can take 10,000 times 12 meters per second quantity squared divided by 2,000 kilograms. And this is kilograms, sorry. And then under the radical is going to give me V. And V is going to equal to 26.8 meters per second. A lot less, but that's because of this guy, that's squared term. All right, that was number 1, chapter 8. Problem 3 reads, objects A, B, and C are moving as shown in figure 8.3. And what we've got here is something like this. We've got A, which is 5 kgs, 5.0 kgs, and 11.0 meters per second. We have B, which is 6.0 kgs. And this is 60. And its magnitude is 10.0 meters per second. And finally, we have C, which is here. It's got a mass of 10 kilograms. And it's got a magnitude of 3 meters per second. And what do we do? Find the x and y components of the net momentum of the particles. If we define the system to consist of A and C and B and C, and then C all 3 objects. So A and C. Let's do it. X sub A is going to be equal to 0, and Y sub A is going to be equal to negative 11.0 meters per second, and then times the mass, 5.0 kg. And this is A and C. And, oh, yeah, X sub C is going to equal to 10 kgs times a -3 meters per second. And Y sub C equals 0. And do I add them or would find just the components? All right, so this is going to be -55 kg meters per second. This is going to be -30 kg meters per second. All right, and finally, B and C. X sub B is going to be equal to 60 kg times 10 meters per second times cos, 6.0, 6.0, not 60, cos 60. And Y sub B is going to be equal to 6.0 kg times 10 meters per second times sine of 60. And let me see what those are. Get out my handy dandy calculator. So clear 6 times 10 times cos 60 is 30. This is 30 kg meters per second. And clear, this is 6 times 10 times sine. That's going to be 51.96, 51.96 kg meters per second. And so I'm doing B and C. So all I have to do is add these. So B and C, I've got a 30 plus, C has an X component. -30, that's going to be 0 and 5, 51.96 meters per second, kg meter per second. That's B and C. Now all three, I'm just going to add them all up. X is going to be equal to 0, right? Let's see. X is going to be equal to 0, right? Because I've got 0 and then plus that and that. So X, so all three, A, B, C, X equals 0. And Y equals -55 minus 30 plus 51.96. No, wait a minute. No, 0, 50, -55 plus 51.96. Sorry. -55 plus 51.96 equals -55 roughly -3.04 is equal to -3.04. So we've had lots of practice doing these kind of separating vectors out into their constituent components and then adding them. And it's not asking us to find the polar coordinates. So it's just asking us to find some of the Cartesian coordinates for various combinations. Okay, number 5 says, one 110 kilogram football lineman is running to the right at 2.75 meters per second, while another 125 kilogram lineman is running directly toward him at 260 meters per second. What are the magnitude and direction of the net momentum of these two athletes and their kinetic energies? Okay, so that's it. All right, so we have the net momentum, P is going to equal to just the sum total of their momentums. They're going like this. They're just coming directly towards each other. So they only have a component in one dimension. So we're going to have P total equals 110 kg, and we'll use going to the right as a positive 2.75 meters per second, and then plus a 125 kg times a negative 2.6 meters per second. And we're going to get a negative 22.5 kg meters per second. And that's that. Now for their kinetic energies. EK total equals 1/2 times 110 kgs times 2.75 meters per second. That's quantity squared. That's the first lineman's kinetic energy. Then plus the second guy's 1/2 times 125 kgs times a negative 2.6 meters per second quantity squared. And it's worth noting that this is a scalar quantity. All right, and we're going to get 838 joules, 838 joules for their total kinetic energies. All right, 811 is a calculus problem. At time t equals 0, a 2,150 kilogram rocket in outer space fires an engine that exerts an increasing force on it in the positive x direction. The force obeys the equation f of x equals at squared, where t is in time and has a magnitude of 781.25 newtons. Oh wait, where t is in time and f has a magnitude, that's a little confusing, of 781.25 newtons when t equals 1.25 seconds. So 781.25 newtons when t equals 1.25 seconds. 1.25 seconds. A, find the SI value of the constant A, including units. What impulse does the engine exert on the rocket during the 1.5 second interval starting 2 seconds after the engine is fired? And C, by how much does the rocket's velocity change during that interval? Assume constant mass. All right, to solve for A, we're just going to use these two values. So we've got a 781.25 newtons equals A times 1.25 seconds quantity squared. So we're going to take that and 781.25 newtons divided by 1.25 seconds squared, and A is going to give us 500 newtons over second squared, which is 500 kilograms meters second squared over second squared. So that's 500 kilograms meters over seconds to the fourth, but it's probably just easier to use these units right there. All right, that was part A. Okay, for the impulse, for B, we're going to use J equals the integral from, what was that time here? 150 seconds, or 2.0 seconds to 3.5 seconds of 500 newtons per second squared times t squared. So that's going to give us 1/3 times 500 newtons over second squared times t cubed from 2.00 seconds to 3.50 seconds. And if you do the math on that, that's going to give you 5.81 times 10 to the third newtons times seconds. And then finally, for part C. Okay, for part C, we know that F delta T equals M delta V, and F delta T is J. So if I take J divided by M, I'm going to get delta V, and that would be 5.81 times 10 to the third newtons times seconds, divided by the mass of the rocket was 2,150 kgs, 2,150 kgs, and I will get 2.1 meters per second. That was 811. 8.14 says, starting at t equals 0, t equals 0, a horizontal net force F equals 0.28 newtons per second, 0.280 newtons times seconds, per second, T I plus a negative 0.450 newtons over second squared times t squared j is applied to a box that has initial momentum P equals negative 3.00 kg meters per second I plus 4.00 kg meters per second J. What is the momentum of the box at t equals 2 seconds? 2.00 seconds. Okay, so what we have to do here is integrate and find the change in momentum from 0 to 2 seconds. And then we're going to add that to the existing momentum at 0 and solve. So let's go ahead and begin. So we're going to take the integral of 0.280 newtons per second times t I, and plus the integral of negative 0.400 newtons per second squared t squared j, and then that's going to give us 0.140 newtons per second times t squared, and that's going to be from 0 to 2 seconds, right? Yeah, 2 seconds. And then that's I. All right. Plus negative, let's see, 4.5 divided by 3 is going to be 0.150 newtons per second squared times t cubed from 0 to 2. And let's see, this is going to give us right here 0.56 newtons per second, 0 newtons times second, 0.56 newtons times seconds. And this guy is going to be negative, that'd be 1.5 times t cubed is going to be negative 0.15, negative 1.20 newtons times seconds. And then we add that to the existing values. And we get this guy plus that is going to give us negative 2.44 kg meters over seconds. And that guy, I, plus 2.80 kg meters over seconds, J. So we took the integral, evaluated it from 0 to 2, and then that we got the change in momentum and added it to the original momentum. Eight 8.2 reads, you are standing on a sheet of ice that covers in the football stadium parking lot in Buffalo. I loved all those little ups and extras. There is, excuse me, negligible friction between your feet and the ice. A friend throws you a 0.600 kg football that is traveling horizontally at 10 meters per second. Your mass is 70 kg. If you catch the ball with with what speed do you and the ball move afterwards? And B, if the ball hits you and bounces off your chest, so it is moving horizontally 8 meters per second in the opposite direction, what is your speed after collision? All right, we're going to use conservation momentum. So for A, we're going to do something like 0.600 kg times 10 meters per second. And then plus you're at 0, you have 0 momentum, you're just standing there, you have 0 velocity, therefore you have 0 momentum. Equals, now you and the ball are going to travel as one little unit, so 0.600 kg plus 70 kg times V final. And V final, I'm going to use, is going to be 0.0850 meters per second. Kg meters per second, kg meters per second. All right. Oh, no, I'm solving for velocity. Sorry. I already have those kgs. All right, so that's that one. All right, now you're going to do B, and now the ball is going to bounce off of you. So you got 0.600 kg times 10 meters per second, and you're still at 0, so I'm not even going to include that term. Equals 0.600 kg times a negative 80 meters per second. That's going in there. Plus U, which you're going to be 70 kg times your velocity final. And that is going to be 0.154 meters per second. So your VF is 0.154 meters per second. All right, so we use conservation momentum to solve 820, I'm sorry, 820. Okay, 835 says, in July 2005, NASA's Deep Impact mission crashed a 372 kilogram probe directly onto the surface of the comet Tempel 1, hitting the surface at 37,000 kilometers per hour. The original speed of the comet at the time was 40 kilometers per hour, and its mass was in the estimated range of 0.10 minus to 2.5 times 10 to the 14. Using the smallest value of the estimated mass, what change in the comet's velocity did this collision produce? All right, let's see. We need to know, okay, we got the probe and we got the comet. So we have let's see, do we know how fast the probe was going? All right, a probe is 372 kg and an hour. So that's this guy, the impact speed, divided by 372 kgs times, plus 10 to the 13th kgs. That's 0.1 times 10 to the 14th. That's what that is. And then the answer is going to be negative 1.4 times 10 to the negative 6 kilometers per hour. All right, and that's part A. Okay, for part B, we're going to do that same deal. Delta V is going to be equal to MA over MA plus MV times the impact velocity, which is V of the comet. No, it's going to be the asteroid now. Asteroid, right? Minus V of the Earth. Anyway, so we know that that's 40,000. So we've got 10 to the 13th kgs. And now we've got to use the mass of the Earth. 10 to the 13th kgs plus, I think it's 590.97 times 10 to the 24th kg. And then that's going to be a negative 40,000. Negative 40,000 kilometers per hour. And our answer is going to be negative 6.7 times 10 to the negative 8th, 10 to the negative 8th kilometers per hour. And that's 35B. $8.48 reads, a 10-gram marble slides to the left at a speed of 0.400 meters per second on a frictionless horizontal surface of an icy New York sidewalk, and has a head-on elastic collision with a larger 30-gram marble sliding to the right at a speed of 0.200 meters per second. Find the velocity of each marble after the collision. Since the collision is head-on, all motion is along a line. And then B, calculate the change in momentum, the momentum after the collision minus the momentum before the collision for each marble. Compare your values for each marble, calculate the change in kinetic energy after collision and minus the kinetic energy for collision for each marble. Compare your values for each marble. All right, so here we go. Okay, since it's elastic, we can use that handy dandy elastic collision equation, which says B 2 velocity V 2 minus velocity of A2 equals the negative velocity of B1 minus velocity of A1. And so we've got, and then we can use conservation of momentum, which will give us and we're going to use the conservation of momentum also. We're going to combine these two equations. 0.0300 kg times 0.200 meters per second plus, so many zeros, 0.01, I'm going to be lazy, kg times a negative 0.4 meters per second equals 0.30 kg times V A final plus 0.01 kg times VB final. All right, going up to the top and solving for this, let's see. Let me solve for, make an expression here. Okay, I know VB minus final minus VA final is going to equal negative VB initial, which was 0.4 meters per second, minus 0.2 meters per second, the negative of that. And that's going to be equal to wait a minute, is this a negative? That's a negative, yeah. So that's going to be equal to 0.6 meters per second. All right. All right, now going up here and solving this guy, I'm going to get an expression that says 3VA final here plus VB final is going to equal to 0.200 meters per second, 0.200 meters per second. And now I just have to add these guys together. If I take these two and subtract one from the other, I'm going to get, finally, my answer will be VA final. VA final is going to equal to negative 0.100 meters per second. And VB final is going to equal to 0.500 meters per second. And that was part one. All right, working with those values that I got there. I've got, let's see, for marble A, marble B, delta P equals MA VA final minus MA VA initial. And let's just go ahead and do that. MA is 0.0300 kg times negative 0.1 meters per second minus 0.2 meters per second. And my answer there is going to be negative 0.009 kilograms meters over seconds. Now for part B, same thing. We'll go ahead and use the mass of B, which is 0.01 kg times a 0.500 meters per second minus a negative 0.400 meters per second. And working that out, we're going to get plus 0.009 kg meters per second. Conservation of momentum there. All right, for the change in kinetic energy, we'll just do for a delta EK A, we're going to get 1/2 times the mass, which is 0.03 kg times V final squared, which is 0.1 meters per second quantity squared minus 0.2 meters per second quantity squared. And I'm going to get negative 4.5 times 10 to the negative 4th joules. And we're going to expect, since it's an elastic collision, a conservation of kinetic energy as well. So EK sub B is going to equal to 1/2 times its mass, 0.01 kg, times the change in its velocity squared, which is 0.5 meters per second, quantity squared, minus 0.4 meters per second, quantity squared. And that will give us the difference, plus 4.5 times 10 to the fourth joules. So we have an elastic collision. We've got a conservation of momentum and a conservation of kinetic energy. Okay, finally, problem 8.62 says a small rocket burns 0.0500, so many zeros, kg of fuel per second, ejecting it as a gas with a velocity relative to the rocket of magnitude 1600 meters per second. So that's the gas ejection velocity relative to the rocket. What is the thrust of the rocket? Would the rocket operate in outer space where there's no atmosphere? If so, how would you steer it? Could you brake it? All right. So to do this, we're going to use the thrust is the force equals the negative velocity of the exhaust times delta M over delta T. That's the change in mass. So we've got, this is going to be equal to negative 1600 meters per second times delta M is 0.0500 kg. Why is it a negative? Because it's losing mass. And that's over 1.00 seconds. And we're going to get plus 80.0 newtons. And as far as B and C go, yes, you absolutely can operate this where there's no atmosphere because it gets its thrust from the dumping of the fuel and the change in momentum. And how would you steer it? You would send off a little boost of fuel to the opposite side where you wanted to turn. And that concludes Chapter 8 homework.